Okay, now good morning friends. After the completion of numerical of illustration, now we start the numerical of exercise. Before starting the numerical of exercise, keep in mind that this number of the numerical of exercise 12.1, 12.2 and additional exercise 12.11 to 12.17. That means the total additional exercise is cancelled for only board exam. Right? Okay. Now we consider the first numerical of exercise 12.1. That's the MCQ type question. Question is that choose the correct alternative from the clues given at the end of each statement. Actually, here the comparison of the Thomson model and Rutherford's model is given in this 5 questions. First is the size of atom in Thomson's model is blank. The atomic size in Rutherford's model. What is the difference of the size of the atom in both models, Thomson and Rutherford? According to each model, either there is a greater than the Rutherford's atomic model or less than the Rutherford's atomic model, or no difference between the size of atom in both models. So first, the size of atom in Thomson's model is blank. The atomic size in Rutherford model. So here there is no different from the atomic size in Rutherford's model. Right? That means the size of the atom suggested by both model, Thomson's model and Rutherford's model are same. No difference. So that is the correct answer. Okay. Now second is in the ground state of blank, electrons are in stable equilibrium. While in blank, electrons always experience a net force. According to which model, in ground state, the electrons are stable equilibrium or in stationary position. According to which model? And according to which model, the electrons always experiences a net force. So according to the Thomson's model, in the ground state, the electrons are in stable equilibrium. No force exerted on this electron. What are the electrons are already in ground state. But here, according to the Rutherford's model, electrons always experiences a net force, in spite of the electrons are in ground state. Because the force of attraction is exerted on this electron are in ground state by the nucleus. Therefore, according to the Rutherford's atomic model, the electron always experiences a net force. Clear? Okay. After that, the next, a classical atom based on blank is domain to collapse. Classical atom based on blank is doomed to collapse. Thomson's model or Rutherford's model. So here, both models are responsible for the classical atom based on both model is the doomed to collapse. Now next is, an atom has a nearly continuous mass distribution in blank, but has the highly non-uniform mass distribution in which model the atom has a nearly continuous mass distribution? In blank model, but has the highly non-uniform mass distribution. So in first blank Thomson model, according to the Thomson model, atom has a nearly continuous mass distribution. And according to the Rutherford's model, has the highly non-uniform mass distribution. So in Thomson model, the atom has a nearly continuous mass distribution. And according to the Rutherford's model, the atom has highly non-uniform mass distribution. Now next, the positively charged part of the atom possesses the most of the mass in. Generally, the entire mass of the atoms and also entire positive charge is concentrated at the small central region of the atom that is known as the nucleus. This concept we discussed in both model, Thomson's model and Rutherford's model. Then the positively charged part of the atom possesses the most of the mass in both model. In both model, Thomson's model and Rutherford's model. So this 5 question is dependent on our knowledge about the Thomson's model and Rutherford's model. After that, the second numerical exercise. Suppose you are given a chance to repeat the experiment of the alpha scattering using a thin sheet of solid hydrogen in place of a gold coin. Right? What is the result you expect? Suppose we are performing this experiment with the alpha scattering from the sheet of the solid hydrogen. Hydrogen becomes the solid at 14 Kelvin temperature. Right? Now, what is the result we expect? Already this experiment of alpha scattering is done, right, by the Geiger master by considering the gold coin. But here, instead of the gold coin, we have given the coin of hydrogen. So what are the results? So first we calculate the mass of the hydrogen atom and also the alpha particle. Now listen, hydrogen contains the 1 proton and 1 electron. Therefore the mass of the hydrogen is mass of the proton, that means the 1.67 into 10 is to minus 27 kg. Hydrogen contains one electron and 1 proton. Thus, the mass of hydrogen nucleus is 1.67 into 10 is to minus 27 kg. That is the mass of the hydrogen nucleus. But alpha particle is made of 2 proton and 2 neutron. So its mass is 4 times the mass of the proton, 1.67 into 10 is to minus 27 kg. That means the 6.68 into 10 is to minus 27 kg. So here the mass of the alpha particle is much greater than the mass of the hydrogen nucleus. So when this alpha particle is incident on the hydrogen atom, so it passes through the hydrogen atoms without diverting, right? Since the mass of is much more than mass of hydrogen atom, hydrogen nucleus. Right? So it cannot throw back. So alpha particle cannot throw back. Cannot throw. So it will pass. So it will pass through the hydrogen atom without diversion. without diameter. Yeah, actually the coil, here the coil of hydrogen coil. When the alpha particle is incident on it, so this alpha particle is easily passed through the scattered alpha particle. That means the scattering of the alpha particle does not take place. Only the alpha particle can pass through the hydrogen atom. Right? So first to calculate the mass of the hydrogen nucleus is, because the hydrogen contains the one proton and one electron, therefore the mass of the hydrogen nucleus is equal to mass of the proton 1.67 into 10 raised to minus 27 kg. While the alpha particle is made up of the two proton and two neutron, therefore mass of the alpha particle is 4 times the mass of the proton. That means the 6.68 into 10 raised to minus 27 kg. When the alpha particle is incident on the coil of hydrogen, so alpha particle is heavier, much heavier than the hydrogen atom. So it cannot reflect back on the thrown back. It will pass through the hydrogen atom without diverting. Clear this thing? Now friends, the next numerical is 12.3. Question is that, what is the shortest wavelength present in percentage of spectral line? Right? What is the shortest wavelength present in percentage of spectral line? For that purpose, what is the general equation of the wavelength? So general equation of the wavelength is lambda IF is equal to R into 1 upon NF square minus 1 upon NI square. Right? Now we know that as we substitute the different value of NF 1, 2, 3, 4 and 5. So corresponding to this value, we obtain the Lyman, Barber, Parson, Bacon and third series. Right? For Parson series, NF is equal to 3, and for shortest wavelength, consider the Ni is equal to E. As the electron makes the transition from larger orbit to the given orbit, at that time the frequency is more while the wavelength is less. For that purpose, the first shortest wavelength, we have to consider the Ni is equal to infinite. Therefore, the lambda minimum, 1 upon lambda minimum is equal to R into bracket 1 upon 3 square minus 1 upon infinite. That becomes the 0. Therefore, I by 9. I by 9. Therefore, lambda minimum is equal to 9 upon R. Value of R is 1.097 into 10 raised to 7. 0.97 into 10 raised to 7 meter. Therefore, we take the reciprocal of this lambda minimum, that is the shortest wavelength for the Parson series is 9 upon R. Therefore, 9 upon value of weight by constant 1.097 into 10 raised to 7. Therefore, the lambda minimum is equal to, as we simplify, we obtain 8.20 into 10 raised to minus 7 meter. So it's equal to 820 into 10 raised to minus 9 meter. That is the 820 nanometer. That is the lambda minimum. So that is the shortest wavelength of the Parsons rays. Again, that is very easy. The equation of the wavelength, general equation of the wavelength, 1 upon lambda IF is equal to R into 1 upon NF square minus 1 upon NF square. For Parsons rays, consider the NF is equal to 3. While for shortest wavelength, NI is equal to infinity. Substituting this equation, therefore we obtain the wavelength is minimum. Therefore, 1 upon lambda minimum is equal to R into bracket 1 upon 3 square minus 1 upon 9 is equal to R by 9. Therefore, minimum wavelength is equal to 9 upon R. 9 upon R 1.097 into 10 raised to 7. So its value is 820 into 10 raised to minus 9 meter. That means the 820 nanometer. Clear? Okay. After that, so this numerical of exercise is also important for the MCQ question and 2 marks question. This is the important numerical. Now, a difference of the next numerical to 12.4 and difference of the 2.3 electron volt separate the two energy levels in an atom. What is the frequency of radiation emitted when the atom makes a transition from upper level to the lower level? Here the energy difference between the two energy levels is given, that is the 2.3 electron volt. When the electron makes the transition from higher energy state to the lower energy state, at that time, what is the frequency of the radiation? We know that E is equal to HF. Energy difference is equal to HF. Verify the frequency. Therefore, frequency is equal to E upon H. E is given in electron volt 2.3. 2.3 electron volt. Convert into joule. So we know that 1 electron volt is equal to 1.6 into 10 raised to minus 19 joule. We have to multiply the 2.3 with 1.6 into 10 raised to minus 19. Divided by Planck's constant 6.625 into 10 raised to minus 34 joule into second. So as we simplify it, so we obtain the 5.6 into 10 raised to 14 volts. 10 raised to 14 volts. Again, in numerical of exercise 12.4, energy difference between the two energy levels is given 2.3 electron volt. When the atom or the electron make the transition from upper level, that is the higher energy level, to the lower energy level. At that time, what is the frequency of radiation? So energy is equal to HF. Therefore, frequency of the radiation is equal to E upon H. E is already given 2.3 electron volt converted into joule divided by Planck's constant. Therefore, the frequency of the radiation is 5.6 into 10 raised to 14 volts. 5.6 into 10 raised to 14 volts. Clear? Now, next numerical of exercise. The ground state energy of hydrogen atom is given as minus 13.6 electron volt. That means when the electrons are in ground state of the hydrogen atom, its total energy is minus 13.6 electron volt. Then total energy of ground state in ground state E is equal to minus 13.6 electron volt. Now the kinetic energy of electron. Now kinetic energy of an electron K is equal to minus of total energy. Minus of total energy. Right? Substitute here, therefore minus into minus 13.6 electron volt. Therefore, kinetic energy is 13.6 electron volt. This is the kinetic energy. Now we have to also calculate the potential energy of the electron in this state. Now, potential energy of an electron is U is equal to twice of the K, twice of the kinetic energy. Therefore, 2 into 13.6 electron volt. Right? But the potential energy is negative, minus double of the kinetic energy. So it's equal to minus twice time of the 13.6 is equal to minus 27.2 electron volt. Again, the ground state energy of hydrogen atom. In hydrogen atom, when the electron is in ground state, at that time it possesses the 13.6 electron volt energy as a total energy. What are the kinetic and potential energy of the electron in this state? Now, the total energy in ground state is E is equal to minus 13.6 electron volt. And the kinetic energy of electron is negative of total energy, is equal to minus of total energy. Therefore, but E is equal to minus 13.6 electron volt. Therefore, kinetic energy of the electron is 13.6 electron volt positive. Now, the potential energy of electron is negative of twice of kinetic energy. Therefore, minus 2K. Therefore, minus 2K is 13.6 electron volt. Therefore, minus 27.2 electron volt is the potential energy of electron. After that, the 12.6 hydrogen atom initially in ground state absorb a photon. In ground state, the hydrogen atom or the electron in hydrogen atom in ground state absorb the photon, which excited it to the 4th level. After absorbing the photon, this electron makes the transition from ground state to the 4th energy level. Determine the wavelength and frequency of the photon. Determine the wavelength and frequency of the photon. Therefore, the energy of electron in nth orbit. Right? Energy of an electron in nth level. There is a En is equal to minus 13.6 upon n square electron volt. Right? Now, energy ground state. That means the n is equal to 1. Therefore, E1 is equal to minus 13.6 electron volt. And in n is equal to 4 level. Total energy of electron in 4th level, or the 4th quantum number orbit, E4 is equal to minus 13.6 upon 4 square. 4 square. That is equal to minus 13.6 upon 16. That means the minus 0.85 electron volt. That's the equation. Now, energy difference delta E is equal to E4 minus E1 is equal to minus 0.85 minus 13.6 electron volt. That means the 12.75 electron volt is the energy difference between the ground state and 4th level orbit. Right? So it's equal to this electron volt converted into the joule multiplied by 1.6 into 10 raised to minus 19 joule. So is equal to 20.4 into 10 raised to minus 19 joule. There is the energy. Now the frequency of the radiation for the photon delta E is equal to HF. Therefore, F is equal to delta E upon X. Delta E upon X. Delta E already we obtained 20.4 into 10 raised to minus 19. That's 6.625 into 10 raised to minus 34. Therefore, the frequency of the photon is 3.079 into 10 raised to 15 Hz. That is the frequency of the photon which is absorbed by the electron in hydrogen atom in ground state. Now we also require the wavelength. That is our first answer, frequency. But we know that C is equal to F lambda. Therefore, lambda is equal to C upon F. C is equal to 3 to 10 raised to 8 upon 3.079 into 10 raised to 15. Therefore, the wavelength of the radiation is 0.97 into 10 raised to minus 7 meter. That means the 97 nanometer. 97.42 nanometer. Again, there is the numerical. Here, the electrons in hydrogen atom in ground state absorb the photon, and after that, it excited to the n is equal to 4 level. Determine the wavelength and frequency of the photon which is absorbed by the electron. First, the energy of electron in nth level, En is equal to minus 13.6 upon n square. Energy of electron in ground state, n is equal to 1. E1 is equal to 13.6. By substituting the n is equal to 1 in this equation, and energy of the photon or energy of electron in n is equal to 4 level, substitute the n is equal to 4 in this equation, we obtain the minus 0.85. What is the energy difference between ground state and 4th level? So delta E is equal to E4 minus E1. That means the 12.75 electron volt. Convert into joule. So 20.4 into 10 is to minus 19 joule. Now, this energy difference is equal to the energy of photon. Therefore, delta E is equal to HF, and F is the frequency of photon. F is equal to delta E by H. H is substituted the value of delta E and as Planck's constant, we obtain the frequency of the photon is 3.079 into 10 is to 15 Hz. But we know that C is equal to F lambda. Therefore, lambda is equal to C upon F. C, velocity of light in vacuum, 3 into 10 is to 8 upon frequency 3.079 into 10 is to 15 Hz. Therefore, we obtain the lambda is equal to 0.9742 into 10 is to minus 7 meter. Therefore, 97.42 nanometer. Clear it?